Hello everyone, my name is Ataberk Olgun and I'm excited to present our work ABACuS, all bank activation counters for scalable and low overhead RowHammer mitigation. Here's the outline of my talk. I'll start with a brief background on DRAM and RowHammer. This is a DRAM module used as the main memory on many systems that we have today. A module consists of multiple chips, each of which contains multiple banks, and each bank is composed of many subarrays. And within each subarray, there's a two-dimensional array of DRAM cells. These cells are organized into rows that are activated using word lines, and the cells are connected to a row buffer via bit lines. Once the data is in the row buffer, the DRAM chip serves read or write requests in cache block granularity. This is a different view of a DRAM subarray that we'll look at to better understand RowHammer. More generally, read disturbance has significant system-level implications because it breaks memory isolation. And RowHammer is a prominent example of read disturbance. Repeatedly activating and closing a DRAM row many times causes RowHammer bit flips in adjacent rows. We call the repeatedly activated row the aggressor row, and the rows that have bit flips victim rows. This phenomenon is getting worse. We can induce bit flips with around 100 times fewer hammers compared to 10 years ago. In other words, the RowHammer thresholds of DRAM chips are reducing. Thus, we need effective and efficient read disturbance or RowHammer mitigations for highly vulnerable systems where only a few hundred activations are enough to induce a bit flip. There are multiple ways to mitigate RowHammer bit flips, each offering a different system design point in the performance, energy, and area trade-off space. Preventive refresh-based ones are promising because they tend to make more efficient use of resources and induce smaller performance and energy overheads. The idea of preventive refresh is to refresh a victim row before bit flips from a RowHammer attack can manifest in that row. That is, preventive refresh essentially resets the disturbance effect. Doing so requires what's called aggressor row activation count estimation or tracking. Activation count tracking or estimation gives us a way of determining when to refresh a victim row. We find that no existing preventive refresh-based mitigation technique prevents RowHammer bit flips at low area, performance, and energy costs. Therefore, our goal is to enable a solution with low area, performance, and energy cost, especially at very low RowHammer thresholds, where activating a row 125 times can induce a bit flip. To this end, we developed ABACuS. ABACuS's key idea, which I will talk about in the next slides, is based on this key observation that we make on how workloads interact with main memory. We will show what we observe over an example. Here's a system with a CPU and 4 DRAM banks. Each DRAM bank has a DRAM row at the same row address, highlighted as with the label row X. A workload running on the CPU generates this load request that targets bank 0 and row X in the beginning of this timeline. Now the CPU issues this request to its target bank and row, and it repeats this access pattern for other banks. There might be other requests that target different rows, but this does not contradict our observation. Eventually, the CPU accesses the same row address across all banks. Now we call the rows with the same row address sibling rows. And there are two causes for this key observation. The first one is the intrinsic spatial locality in workloads' memory access patterns. A program usually accesses neighboring cache blocks at around the same time, and a prominent access pattern that leads to this behavior is streaming through the elements of an array. The second cause is the modern physical address to DRAM address mappings that place neighboring cache blocks into different banks but into the same DRAM row. They do this to leverage bank-level parallelism and get the most out of the available DRAM data transfer bandwidth. Now, this plot pictorially depicts our key observation across many tested workloads. I will not explain this in detail in the interest of time. When a row gets activated RowHammer threshold times, which is 500 for this figure, we record the activation counts of each of that DRAM row's siblings. And each box in this plot shows the distribution of sibling rows activation count for a tested workload. Above the horizontal green line in the figure shows that if a row is activated RowHammer threshold times, its siblings are activated more than half the RowHammer threshold times. Therefore, if we can track the sibling rows that is activated the most, it could give us a good estimation, or it could give us a good estimate for the activation count of all of its siblings. We repeat this analysis for smaller RowHammer thresholds, and you find that the key observation is more prominent as the RowHammer threshold reduces. Let me now quickly introduce an important problem of existing per bank activation count-based preventive refresh-based mitigation techniques. There are many banks in a DRAM chip, and the number of banks, and thereby the number of activation counters, increase with newer DRAM generations. We have seen that sibling rows have similar activation counts, so our key idea is quite simple. It's to use one activation counter for all sibling rows and reduce the number of counters by a factor of the number of banks in the system. ABACuS's objective is to track the maximum activation count across all sibling rows using one counter. If, for example, the activation count of sibling rows look like this, then ABACuS's counter value for the sibling rows will either equal or be larger than 97. Why? Because if the ABACuS counter is smaller than the maximum activation count, we cannot mitigate bit flips. And if it's larger, we will have increased performance and energy overheads from unnecessary preventive refreshes. And because of these two reasons, our key design goal for ABACuS is to keep its counter value equal to the maximum activation count. I'll quickly explain the intuition behind ABACuS's counting algorithm. This diagram depicts an example system state where sibling rows have different activation counts from each other, and the maximum activation count is in bank 15. We will assume that ABACuS currently stores this maximum activation count. Now, ABACuS remembers that the sibling row that last got activated and increased the counter value to 97, which is bank 15 in this example. Now, at this point, two different actions can increase ABACuS counter value to 98. The first one is when the bank 15 gets activated again. The second one is if any other bank gets activated twice. I'll leave you with this much detail about how ABACuS operates in the interest of time. Now, ABACuS needs a small additional state of 1 bit per bank to operate in this way, and we prove in our paper that ABACuS correctly maintains the maximum activation count using only one counter. Our implementation of ABACuS leverages a prior work, namely Graphene's activation count tracking algorithm, and for more details on how we implement ABACuS, please check the paper. Now let's see how ABACuS performs. We use a cycle-level memory system simulator configured in the way that I show you here, and we compare ABACuS to 4 state-of-the-art preventive refresh-based RowHammer mitigations. These are namely Graphene, Hydra, Rega, and Para. Graphene is the highest performance mechanism, Para is the lowest area overhead mechanism, and Hydra and Rega offer interesting trade-offs between area and performance. We simulate 62 single and 8 core multi-programmed workloads from major benchmark threads. We show the system throughput on the y-axis across all single core workloads for the RowHammer threshold values displayed on the x-axis. The higher the bar, the better the performance. And this is the DRAM energy overhead. Here, a smaller value is better. We conclude that ABACuS prevents bit flips with very small performance and DRAM energy overheads compared to a baseline system that has no RowHammer mitigation. This plot will eventually show 8-core multi-programmed performance distribution across all workloads on the y-axis for ABACuS and the 4 state-of-the-art mitigation techniques. Now here, higher values indicate better system performance. This is the full plot. Here are the boxes for ABACuS showing the distribution of performance across all tested workloads. And the red boxes here show you the mitigation and RowHammer threshold configurations that ABACuS outperforms. We observe that ABACuS outperforms Hydra and Para at all RowHammer thresholds on average across all workloads. We also see that ABACuS incurs a small performance overhead over Graphene, which we attribute to ABACuS's unnecessary preventive refresh operations due to its low-cost aggressor row activation tracking scheme. Here's the same plot, but for DRAM energy. We observe that ABACuS consumes less energy than Hydra, Rega, and Para at the tested RowHammer threshold smaller than 1000. For example, ABACuS consumes approximately 20%, 70%, and 34% less energy than Hydra, Rega, and Para at a very low RowHammer threshold of 125. ABACuS performs similarly to Graphene in terms of DRAM energy, that is only 4% higher at the same very low RowHammer threshold. We analyze ABACuS's area overhead, and we observe that at a RowHammer threshold of 1000, ABACuS induces a significantly smaller area overhead than Graphene, and it takes up smaller area than Hydra. At a smaller RowHammer threshold of 125, ABACuS takes up significantly smaller area than Graphene, but Hydra's area overhead at this very low RowHammer threshold is relatively smaller than ABACuS. But compared to ABACuS, it induces a significant performance overhead, as I showed you in the previous slide. We exclude Rega and Para from this analysis because they don't incur processor chip area overheads. However, Rega requires intrusive DRAM chip modifications, and Para needs a secure random number generator. We have more details and analyses in our paper. The paper presents a security analysis of ABACuS, which shows that it guarantees to track the maximum activation count among all sibling rows and securely mitigate RowHammer bit flips. Performance and energy comparison for less memory-intensive single-core workloads. We have circuit-level performance, latency, energy, and power estimation based on a functional hardware Verilog model of ABACuS. For example, we show that ABACuS' circuit latency is approximately 1.2 nanoseconds, which is significantly smaller than the minimum allowed delay of 2.5 nanoseconds between two activate commands. ABACuS' performance under adversarial workloads that aim to exacerbate preventive refreshes by rapidly incrementing ABACuS counters, and our alternative ABACuS design that defeats these workloads. We have ABACuS' performance and energy sensitivity to important system variables. And finally, we have a discussion on how we can account for row press, which induces bit flips by keeping a DRAM row open for longer rather than repeatedly activating it. I invite you again to read our paper for these details. Now I'll quickly conclude my talk. Based on the key observation that many workloads access the same row address in different DRAM banks at around the same time, we developed ABACuS, which uses one counter to track the activation count of many rows with the same address across all DRAM banks. We show that ABACuS induces small performance and DRAM energy overheads at very low RowHammer thresholds, such as 125, and we show that it outperforms state-of-the-art mitigation techniques. An extended version of our conference paper is available on arXiv, and all our data and sources are open source and artifact evaluated. That will all. Thank you very much.